today's class we will discuss how to use resistance measurement effectively in case of temperature control and temperature measurement. So, for this example we pick up platinum resistance thermometer and show how this resistance change is measured to indicate the temperature. We will see in two domains, one is in voltage output producing circuit, in another case current producing circuit, that is 420 milliampere current source as a temperature measurement, another one is a voltage as a temperature measurement. So, we will take a PRT as a temperature sensor. So, we use platinum resistance thermometer, resistance thermometer we use as a temperature sensor. So, essentially what we are going to do is we will take PRT and then we apply a constant current source. For example, we have a constant current source and then current source is applied to the PRT and then we will make a 4-wire method. So, this will be made as a voltage measurement. So, essentially you have 4 leads, that is one current lead, second is a voltage lead, third is a voltage lead and then fourth is a current lead. So, 4-wire technique we use to measure the temperature and this is the PRT, platinum resistance thermometer. So, as I said, we use two methods, that is one is what we do is in one case I use the PRT and then use a simple voltage amplifier. For example, you have the plus 15 volt and then you have the PRT and then this PRT will be connected in a 4-wire method to instrumentation amplifier. Then output of the instrumentation amplifier gives you the temperature. Of course, this is to be the voltage to be subtracted in case if you want to make a temperature measurement. So, the base voltage has to be subtracted. So, that has to be done, that is in one case. So, case 1 voltage based measurement. And then in case 2 we go for 420 milliampere current based measurement. So, case 2 current based measurement, 420 milliampere current based temperature measurement. For this what you do is we will have the current source, then similar arrangement, then we have a difference amplifier, then we have the level shifter, then we have the level shifter output is given to the current converter. So, V to I converter and then the whole thing is integrated to the input 420 milliampere with a voltage regulator. We will have a voltage regulator that is given here and that will act as a input. So, we will see one by one how these two systems works. First we pick up 420 milliampere current based temperature measurement. So, we will see for 20 milliampere temperature transmitter. Using PRT. So, in this actually the input is 24 volt DC, 24 volt DC 2 wire system, 24 volt DC. The output is 420 milliampere current. Of course, the transducer is PRT, and we keep temperature range as 0 to 400 degrees C, and then ambient temperature range that is the instrument working range, that we take -20 degree to 80 degrees C, industrial grade equipment, and then what the accuracy that we are aiming is 1%. Accuracy is plus or minus 1%. That is what we are actually aiming at. Plus or minus 1%. So, what we do is we will take 24 volt DC as a input supply, and then we use platinum resistance thermometer, as a temperature sensor, and then the platinum resistance thermometer resistance changes 0.4% every 1 degree temperature, that it is a positive temperature coefficient. Resistance increases by 0.4% every 1 degree increase in temperature. So, the what we do is we will pass a constant current through the PRT. So, that change in voltage will be reflected as a change in resistance will reflect as a change in voltage, because resistance of the PRT changes with the temperature. We are passing a constant current. So, net result is the voltage across the PRT will change with temperature. That voltage will be converted into 420 milliampere current to indicate the temperature, and the temperature measuring range is 0 to 400 degrees C, and this instrument is supposed to work -20 to plus 80 degree, and we aim for 1 degree accuracy. Let us see how to go about designing the circuit. So, the input is 24 volt DC. So, the input only on the input only we will be connecting the measuring instrument also. So, essentially the 24 volt DC, so input supply looks connected like this to the system. So, you have a 24 volt DC supply, and it is connected through a long wire, and then you have our electronic circuit coming here. And this circuit, to this circuit the PRT is connected. It is a 4 wire method. So, we will have 4 points, voltage, 2 current point, voltage points and 2 current points. So, this is I1 and I2, and the 2 voltage points are V1 and V2. So, 4 terminal connection is made, and this is actually the current transmitter, 420 milliampere current transmitter. Of course, this has the adjusting potentiometers. So, one for 0 and another for span, 0 and span. That is these 2 potentiometers are required to make sure that the current flowing through this, because the current flowing through this is going like this, and then while making measurement they will connect here up to 600 ohm resistance. The voltage across this is measured. So, this voltage gives you the temperature information. For example, when the temperature is 0 degree C, we adjust this 0 part to get 4 milliampere. So, at 0 degree C, current is 4 milliampere. At 400 degree C, the current will be 20 milliampere. So, this current actually this current 4 milliampere to 20 milliampere varying. So, 4 milliampere at 0 degree C of the PRT, 20 milliampere at 400 degree C of the PRT. So, corresponding to that we will have a voltage at 4 milliampere, we will have 600 ohm into 4 milliampere, we will have 2.4 volt. So, essentially means at 0 degree C we will have 600 into 4 milliampere 2.4 volt. At 400 degree C we will have 600 into 20 milliampere, that will be 12 volt. So, voltage across this I will indicate the temperature status of this one, because this is attached to the oven or whosoever oven or any other object whose temperature to be measured. So, essentially this temperature is indicated as a voltage across this. These lines can be few kilometers, that is what happens in the industry, that in a process control industry this will be actually in the field and this will be in the control room, and the distance invariably goes a few kilometers, and you see that the temperature is correctly reproduced, the voltage here correctly gives you the temperature indication of this the object which is attached to this. So, this is actually a popular 420 milliampere system, and the 0 and spans are used to adjust such that at 0 degree temperature of this you get 2.4 volt here, that is the current will be 4 milliampere, that is adjusted using this, and then keep this at 400 degree C and then adjust the span to get exactly 20 milliampere through this. So, at 400 degree C you will get here 20 milliampere, if not you adjust this. So, 0 and span are repeatedly adjusted such that at 0 degree C you get 4 milliampere current through this, at 400 degree C you get 20 milliampere current this. So, this is the 2 potentiometer that is required for adjustment 0 and span adjustment. So, this is the system that we have to design now. So, we start our story from the supply. So, if we take the supply here, this supply voltage normally given as 24 volt supply, but this gas invariably varies plus or minus 10%. That means, it may go to 26.4 at the higher side and minus side 2.4 volt down, that is 24 minus 2.4, that comes 21.6. And similarly, the resistance also they may not keep all the time constant, the resistance also they vary from 100 to 600 ohms. So, the variables here are in this design: 1 supply voltage variation, that is from 21.4 to 21.6 to 26.4 volt, and then load variation. Load can vary from 0 to 600 ohms, not more than 600 ohms. So, while designing we have to consider these two factors as well, because the voltage the battery may not be constant, and different people use different load. Some people use only few ohms, some people may use full 600 ohms. So, one have to consider this, because varying the load makes the suppose the current is 20 milliampere, then if 600 ohm is put, then you will have 12 volt drop here, and if this is 24 volt, if the input is 24 volt, then you will have only 12 volt appearing here, because 24 and here 12 volt gone, only 12 volt will appear as a supply to the instrument. Whereas, if another person uses 100 ohms, then for same 20 milliampere you will have only 2 volt drop, and in that case you will get 22 volt across this. So, variation of the supply and variation of the load changes the available voltage to the current transmitter. So, that is an important consideration while designing the circuit. So, the variation of the load. So, the variation of the load and the variation in the 24 volt supply 24 volt supply where is the available voltage to the transmitter, voltage to the current transmitter. So, one has to consider this factor while designing this. So, so essentially the supply voltage varies to the current transmitter. So, to tackle this we had done earlier voltage regulator circuit for this. So, the same thing can be adopted in this. So, one can relook at this one. So, we have designed the earlier the circuit for this 420 milliampere current transmitter, the same circuit we use now here. I will not spend much time on this, I will just show you how this regulator is made. So, you take this voltage, then we will have a regulator in here, and then we have used error amplifier for this purpose. So, operation amplifier was used as an error amplifier, and then we also had used one Zener to start up the current. So, we have put this, then we have put very high resistance to bias to give a base current to the transistor. Then the output of that is actually used a voltage divider, and then we connected this, then we have connected this to minus, and the plus input we had given the reference voltage. Biasing the reference voltage was done using this, and supply for this op amp is drawn from here, and you will get and then we also put a small capacitor, I don't know, 1 mF, so that this voltage is regulated. So, we take 0, maybe since the voltage at this point, that is available voltage can go down as low as 10 volt, because it is 24 volt, some of them will be lost and the load resistance, and this voltage also can go 22. So, essentially you will get only around 10 volt reliability. So, we will make it the circuit work up to 7 volt or so, we get a regulated voltage. So, we can adjust the voltage to get a 7 volt. For example, we can have 2.5 volt Zener here, and then we can adjust this values can be selected this, and this can be adjusted to get 7 volt, and this can be selected for a required bias current. For example, if we need 2.5 volt 50 microampere current, in that case this resistance can be selected such that the output is 7 volt. So, V0 is 7 volt. So, this is R1. So, R1 will be 7 minus 2.5, because this is sitting at 7 volt, this is sitting at 2.5. So, the voltage across 7 by 2.5, and the minimum current required for the Zener is say 50 microamps. So, that is the resistance that we had to take. That comes, for example, 4.5 volt divided by 50 microamps. 50 microamps, that comes close to say 82 K resistance we will do for this purpose. So, we will have 82 K resistance, so that the current drawn by this is limited to slightly more than 50 milliamps, and then we can take this 100 K, then this R2 can be selected such that output is 5 volt. So, we can calculate the value of R2. So, voltage across say R3 is 2.5 volt. So, the current actually comes 2.5 by R3 and same current flows through R2. The same current is flowing through R2. So, current through this is now going by 2.5 by R3 and the same current flows through this. So, the voltage across this I into R2 plus this voltage. So, essentially means output voltage will be V0 is given by 2.5 by 100k into 100k plus 100k plus R2. So, R2 can be calculated. So, by fixing the required R2, one can get 7 volt that is required at the output. So, you will get a regulated voltage as we explained earlier, and this zener is used. This zener is used because the circuit have to start initially, because initially the voltage here is 0. So, if 0 voltage is there, the op amp is not going to work. To make the circuit work, we have biased this using this. So, we have put for example, here I resistance say 470k. So, whatever current that is coming here, it has to go through this, and then small voltage there, that whatever voltage is there, few volts, it need not be zener breakdown voltage. More than 1.2 volt present here, then the voltage comes out here, and that makes this voltage that much go high, and that also increases this, like that slowly the voltage builds up and stabilizes to 7 volt. So, the zener is not for breakdown, it is not operating the breakdown, it is only to provide a initial voltage such that the circuit starts. So, and you need a Darlington such that the base current is negligible. So, that we able to put I resistance here. If we put I resistance only, we will have less current variation through this when the supply voltage changes. So, this is the first part of this design, the voltage regulator, which we had done earlier also in the 420 milliampere source. Now, from this source, the regulated source as a basis I will take, and then I will build up the constant current source plus the other circuits to go with Platin thermometer temperature sensor. So, we will have now voltage source, then we had this regulator here. I will skip the other part of the circuit, I will keep only the output here, and then the regulator output is coming here. So, the other part I skip it here, and you have a regulated output voltage say 7 volt or 8 volt, whatever is required, you can achieve this. Then this supposed to be given to a Platin thermometer. So, what we do is we have to make a constant current source. One possible constant current source is this, that I can have okay, we need only a small current. So, we need not have a transistor to drive this. So, one possible current source would be we can have input voltage we can have a possible current source. And this is supposed to be given to V reference, and we have here the V reference in the, this is grounded, and in the regulator we have on V reference 2.5 volt. The same 2.5 volt can be utilized if the current drawn is small. If the more current required, one can adjust readjust this resistance, because if you need more current through this and then this current to be increased, in that case we have to reduce this resistance to supply the required amount of current to this, but normally this resistance can be kept high, so that this current is negligible. So, one can have a current source like this. So, this current source output supposed to be connected to PRT. this is pattern resistance thermometer that is to be connected here. So, the current in this is I is given by, if this is V reference and this is R, and we have these 4 resistance equal, well, particularly I value resistance, you have 100K, for example 100K and then 100K, all 4 must be equal. So, this kind of constant current source we have discussed earlier in connection with some other circuit. So, the current that is flowing through this is constant, and that current is given by VR by R. So, here we have to select the current I, because the current I that is flowing here should not be too much, because we do not have more current. The total current available is only 4 milliampere. So, this current can be kept to 0.5 milliampere, or at the worst it can be maximum 1 milliampere, not more than that. That higher current also creates problem, because higher current also will heat up the device, and we will have more issues with that later. So, we keep the current I as say 0.5 milliampere. So, I actually what is allowed is 0.5 milliampere. So, the so I actually is given by 2.5 volt divided by this resistance R, which is 0.5 into 10 power minus 3. So, the value of R can be computed 2.5 divided by 0.5 into 10 power 3, that comes 50K. So, we need a 50K resistance. So, 50K here 0.5 in 10 power minus 3 become 10 power 3. So, you have that is 5K, this is this will be 5K, this is 5K. So, we need to have R as 5K here. So, 5K resistance will make sure that the current flowing through this is only 0.5 milliampere. So, normally pattern resistance thermometer of 100 ohm is what is used, pattern resistance thermometer of 100 ohm pattern resistance thermometer is used, that actually makes 100 ohm into 0.5 milliampere. At the lowest you will have 0.5 volt across this. This 0.5 volt is good enough for most of the single supply op amp circuits, because higher the voltage, then we will have more issues in reducing the voltage later when we want to convert this voltage into current. And similarly, if you have a higher current, keeping higher current also is an issue, because higher current will make this device to heat up, because we are measuring the temperature, and the current itself should not heat the pattern resistance thermometer. This is called self heating. To limit the self heating also, we have to reduce this current. I explained already the working of the circuit in connection with some other design, that essentially this is acting as a voltage follower. So, that this voltage is whatever voltage is here is put up at this point, and whatever voltage is there, it comes here. So, we know that voltage at this point must be equal to this point. So, if the more current flows through this, voltage at this point decreases, that makes this voltage decrease, that makes the output to decrease. And similarly, when the current is less, then equivalent telling this voltage is going up, and this makes this to go up, and it will push this output voltage high. Like that, the current is self regulated, and you will have a constant current source, with this arrangement. Now, this voltage that is there across this resistor should be converted into current. So, we said we will use a 4-wire method. So, what we have done is, now I will pick up from this current source onwards. So, we will have this so far the current source, that is nothing but this op amp circuit. So, this op amp circuit gives you the current, and this is the regulator part. So, here is the, if we draw this, PRT more is, so what is normally, this is a very long wire going in, and that is the resistance coming back, and then we have to take up the voltage between these 2 points only for measurement. That is why 4 points, 1, 2, 3, 4, and this voltage should be converted, this voltage is a converted differential voltage. So, normally what is done is, to convert we will use a difference amplifier. So, this is at higher potential, this is at lower potential. So, one can do this, or even one can do in a, we can have a difference amplifier first. So, one can have this, and then if this is grounded, then the difference between these 2 points will appear across this. So, the difference between these two, for example, if it is 100 ohm, say at 0 degree C, then you will have 0.5 volt difference across this, and if these resistances are equal, then you will be getting 0.5 volt, the minimum voltage. But one small issue in this is that if it is a single supply op amp, if this op amp is operated in a single supply, because we are making 420 milliampere current transmitter. So, this op amp is invariably operated in a single supply. So, you have a ground here and then plus 5. If this is if this point is at 0.5, then this will be 2.5 volt, and this also will be 2.5, no 0.25 volt. If this is 0.5 volt, then this is 0.25, this is also 0.25. Most of the single supply op amps accept 0.25 volt, like LM324 accepts 0.25 volt. So, one can use this arrangement, there is no problem. So, you will get the 0.5 volt at the output. Output also, most of the single supply op amp like LM324 gives you up to 0.5 volt linear output. So, no issue with that. Only worry would be this 0.5 volt may be too small for the next stage, that is, we are convert this into a current. So, to solve that problem, what we can is, we can instead of grounding it, we can float it at some fixed reference voltage. That can be done by modifying this. So, what can be done is, this 100K, I can give it to a potentiometer which is 2.5 volt here. This can be obtained from reference voltage which was used in the earlier case. So, you will get for example, this can be high 100K potentiometer. So, one can keep this one at whatever point we want. For example, if the difference is 0.5 volt here, for example, if the difference is 0.5, because this is 0, this will be 0.5, and if this is kept at 0, if this is kept at 0, then you will get 0.5 volt. So, output if I keep it 1 volt, then output will also be added to 1 volt. So, the output voltage I will mark it now, V difference I put it here, this is V difference, and this is V 0. This can be used as a 0 adjustment. So, if I take V 0, then the output at op amp is given by V 0 is given by V difference plus V 0. So, whatever, if it is in this case, it is Vd is 0.5 volt, the voltage across the plate resistance thermometer is 0.5 volt, this is 0.5 volt, we have kept this one say 1 volt, we keep this one 1 volt, then output will be 1.5 volt. So, one can adjust this to get whatever voltage we want. Nevertheless, if the temperature changes, the resistance of this changes,
because of that the voltage across this will change. For example, at 400 degree C, the resistance would have gone up by okay, I will complete this first. That is, you have the output will, for example, if it is 1 volt plus V0 is 1 volt, then the V0 will be, output voltage will be 1.5 volt. So, by adjusting 0 part, one can vary the output voltage. Zero part, we can vary the output. We can vary the output voltage, because this is required later in our design, that we have to vary the this voltage depending upon the requirement. So, this 0 adjustment is required. So, only thing is, now we have to estimate what is the expected output voltage here at when the temperature of this goes to 400 degree C. So, for this we have to find out what is the resistance change. So, PRT resistance, PRT resistance value at 0 degree C is 100 ohms. So, PRT resistance at 400 degree C, that actually 100 ohms plus 0.4% it changes, 0.4 ohms by 100 into 400. 0.4% it changes 0.4% into 100 ohms. So, that actually gives 0.4 ohm into 100, that will actually become 260 ohms. So, at 400 degree C, the PRT resistance will become 260 ohms. Then, so the voltage across that will become correspondingly more. So, at 0 degree C, PRT resistance is 100 ohms, and then the voltage across PRT will be 100 into 0.5 milliamps, 100 into 0.5 milliamps, that will be 50 millivolts, sorry, it is 50 millivolt. Yeah, our actually our assumption of 0.5 volt here, there is a small mistake, it is supposed to be 50 millivolt, because if 0.5 milliampere is going through this, 0.5 milliampere into 100 ohms will give you 50 millivolt, and then 50 millivolt at this point will make 25 millivolt here. So, in that case we had to use op-amp like LM10 to accept this level of voltage, and you will also get here 0.5 50 millivolt only. So, this is actually to be modified as 50 millivolt, this will be 50 millivolt, and this will be 1.05 volt will be the output voltage. So, we are wrongly taken as 0.5 volt, it is actually 50 millivolt is what it is coming, plus this voltage to be added up here. So, if we take this one, then it is at 50 millivolt, then at 400 degree C, PRT resistance, because PRT resistance equals 260 ohms, and the voltage across that PRT will be 260 into 0.5 milliamps, that becomes 130 millivolts. So, the voltage across this goes to 130 millivolt at 400 degree C. So, correspondingly the output voltage, if you look at the output voltage at this point, so we can rewrite this. So, output at this point 50 millivolt plus V0 at 0 degree C. At 400 degree C, then this becomes 130 millivolt plus V 0. So, that is the net output at this point. So, you will have about 80 millivolt variation at this point. One can also design the circuit for 1 milliampere current. In the case, for example, if we design the circuit for 1 milliampere current for PRT excitation of 1 milliampere, then V 0 will be 100 millivolt plus V 0. This is at 0 degree C. Then V 0 will be 260 millivolt plus V 0. This is at 400 degree C. So, one can select the current even if required for 1 milliampere as well, because we will able to use slightly low cost op amp when the current, if you increase the current, because the op amp need not go down to such a low working voltage if you are using, and also drift will be less if the excitation current is more, and 1 milliampere current is actually possible to use in this design. So, we will get the V 0 here at this point depending upon the current that we have selected. Now, the next stage is this voltage to be converted into 420 milliampere current. So, this is to be connected to the next stage, which is the current converter stage. So, I will redraw this circuit now. So, this output of this difference amplifier, this is where the PRT is there, and the PRT terminals are connected here, and this is where the PRT 0 part is connected. And this is given to 2.5 volt. This is 0 part, and these resistors are essentially to be same 100 case or 470 case also okay to reduce the current drawn by the circuit. So, one can have this, and this output gives you voltage corresponding to the temperature, that is we had seen in the case of this thing 100 millivolt plus V 0 or 260 millivolt plus V z at 400 degree C. So, this is the voltage that you get at 100 degree C, this at 0 degree temperature of this, and when this is at 400 degree C, you will have 260 millivolt plus this V z. This V z is this voltage what we have fixed it here. As I said, this is required, the V z need to be added, so that one will easily design the next current converter stage. So, now we will go and design the current converter stage. So, for this what you do is you will take the operation amplifier, and this need to drive the current. So, we can have even Darlington pair for driving this. Now, it would be easier to go with the similar current source in this case, because what we can do is we can have fixed resistance here, and then we can have a span part across this connected. So, this is Rx is a fixed resistance, and this is R span, and this is supposed to go to the 7 volt regulated supply. Then if this voltage increases, we want the current to be increased. So, I can connect this to this point. Then I have to connect for example, in first case I can connect this the voltage of this one, then we do not want the voltage loss across this. So, I can always have voltage follower connected to this. Voltage follower connected to this point, and this can be connected to this. Now, this is connected to ground, and we have the same arrangement which what we had earlier. The same current source can be now used to get 420 milliampere current depending on this voltage. So, we have for example, here we can have all resistance equal. Example 100 K, and we know the for example, for a simpler argument we can have for example, I remove this, I put the thing straight away here, then current through this. So, current through this I is actually given by this voltage, say I call Vx by Rx. Current through this is given by this Vx by this resistance value. There is a small change here. This is supposed to be connected to this point. So, we can have select the Rx, and this can be any resistance, there is no problem, we can have equal to Rx or it can be any other value. So, essentially what happens, the current flowing through this now determined by this Rx and Vx. So, the current flowing through this is can be selected such that when the lowest voltage, that is at 100 millivolt plus Vx, the current is roughly about 4 milliampere total. So, that is for total means this current plus all the rest of the current put together should not take more than 4 milliampere, maybe about a milliampere current can be taken. That means at this voltage level we need 1 milliampere current, and at this voltage level we need around 17 milliampere current, assuming 3 milliampere is drawn by other circuits. So, we assume assuming 3 milliampere current is drawn, by the rest of the circuit. We have to fix I equal to 1 milliampere at 100 millivolt plus Vz, and I should be equal to 17 milliampere at 260 millivolt plus Vz. Now, this is a nonlinear relation. So, we have to arrive at this voltage, then we have to carefully select the biasing arrangement, because now the current is given by 100 millivolt divided by Rx. So, this current has to vary 1:17, whereas this voltage is varying only by 1:2 or 3. So, by adding Vx, in fact, the change even comes less. So, one have to add this dead voltage suitably to solve this issue. So, one can add the dead voltage at this stage, actually one can put the required voltage at this stage. One possibility is that one can have large resistance drawn here, and then we can put this to V reference. So, that voltage at this point, if I taking this as all resistance and this is a very small resistance, then one can get voltage at this point contributed by two factors, that is this is y. If the voltage is y, then for example, if I have equal resistances say 100k, then VR plus this are added together. So, by adding a suitable voltage at this point, one can get the voltage at this point, that will that actually will be added with this. Now, one problem with this is that we already having excess voltage, that will call for this minus voltage to be adding at this point, that is not a practical solution. So, minus voltage is not available at this point. So, the technique of adding the voltage at this point may not work, because we do not have minus voltage. If minus voltage is there, one could have subtracted the voltage and got the minus, and that would have subtracted here. Now, other possibilities, keep this voltage as 0, that the 0 voltage can be kept here as 0, and then you will have 100 to 100 millivolt to 260 volt only varying, that can be made to vary 420 milliampere, that is another possibility. Now, so to make it 420 milliampere, we can do but then keeping this 100 and 260 millivolt varying 420 milliampere is not a easy solution, because that ratios will not match. One have to do lot of jugglery in terms of resistance variations, or other possibilities we can also add the voltage at the plus input. So, one can add the voltage at the plus input, like instead of adding it here, I remove this, I can also add voltage at this point, because the plus voltage adding at this point will make this voltage to subtract. So, one can add, for example, the plus voltage can be added to this. So, one can also keep plus voltage at this point. So, one can do this by putting one more operational amplifier here. I can have V reference here, and the output of this can be connected to this. By connecting this output, so you will get this required voltage can also be varied by varying this resistor. So, any voltage you want, this is because your 2.5 volt zener is there. So, whatever voltage you need, that can be tapped by varying these two resistors. So, by adding additional voltage at this point, we can take care of this extra 100 millivolt or this Vz whatever is there, that can be tackled, because most of the op amps may not go down to 100 millivolt. So, it is also essential to add this Vz at this point, so that the minimum voltage requirement is taken care. So, this arrangement works all right. Only thing is we have to adjust this say voltage Vi to be correctly calculated such that you get the required voltage. Now, the current is given by Vx minus Vi divided by R is coming as I actually. So, one can select the Vi such that we will get the required quantity, because Vx if we take, that varies from 100 to 260 millivolts. So, if I take this Vx variation is given by 100 millivolt plus Vz at 0 degree C, and that is equal to 260 millivolt plus Vz at 400 degree C. So, one can select Vi such that this Vz plus 100 millivolt is can be taken care, such that I can now write it. For example, we want 100 millivolt plus 100 millivolt, assume Vz is 100 millivolt, then I will get if I take Vz as 100 millivolt, then we get 200 millivolt, Vx equal to 200 millivolt at 0 degree C, and then Vx equal to 360 millivolt at 400 degree C. For example, if I want total current as 1 milliampere, then what I can do is Vi can be taken as, Vi can take such a way that, for example, assuming R as 100 ohms. So, 200 millivolt, if I substitute in the equation, you will get 200 millivolt minus Vi divided by 100 should come as 1 milliamps, and then that will come as Vi. For example, Vi will be equal to 100 millivolt, that will give you 1 milliampere current. Then at 260 millivolt, for example, Vx is 360 millivolt, at Vx equal to 200 millivolt, we will get Vi is equal to 100 millivolt for Vi is equal to for Vi is equal to 100 millivolt, then for Vi is equal to 100 millivolt, then I will be equal to 1 milliampere. For Vx equal to 360 millivolt, for Vi is equal to 100 millivolt, then I will become 260 divided by 100, that will be 2.6 milliamps. So, this ratio can be made such that this is coming as 1 milliampere and this comes as 17 milliampere. One can do this by alternatively adjusting Vi and R, because we have the option of adjusting Vi, Vx and R, all three parameters can be adjusted such that at one end I comes as 1 milliampere, at the other end it comes as 17 milliampere. So, this exercise I leave it to you, you can perform this. So, one can adjust this by adjusting Vi and R, and then as well as V0 actually V0 plus you can adjust adjusting V0 and then adjusting the voltage, that is Vi, and then adjusting this Rx, actually this Rx is not R, so it is Rx. So, one can adjust these three quantities such that you can get one end 1 milliampere and the other end 17 milliampere. So, one can get 1 milliampere at 0 degree C and 17 milliampere at 400 degree C. So, that will make the entire circuit work as if it is a 420 milliampere current transmitter. We can add together the entire circuit and make it as a single circuit in the next class, so that you can understand as a complete circuit how this 420 milliampere design works. Thank you.